Speaker again. And now the next speaker is Brianna Marshall for specifying ABIs with realizability on time-preserving compilation.
Okay, yeah, thank you very much. Right, so I'm going to talk about, first let's start with some setup of if you have two programs written in different languages and you want them to talk to each other, you usually use an FFI for this purpose. And how this works is you interact with the languages at the source level using FFI that gives you a set of types, and you compile those down to your final executable format. And then at this binary format, you can link them together. And so usually how this works is that the FFI is almost always based on C types. And those compile down to a C-based ABI, application binary interface, at the target level. And so the advantage of using C types for the FFIs is that it's a widely supported, stable ABI, which is nice because it's widely supported so that you're pretty much guaranteed that any two languages will happen to understand C, and that so they can use that as their common language. And it's good that it's stable because you need that for dynamic linking between packages that update independently. But C's type system is quite impoverished, and so this leads to some issues when you want to communicate between two languages that neither language is C, and they have rich type invariants as part of their type system. So for example, you want to share memory between OCaml and Rust. And so on the OCaml side, you have a reference, which is garbage collected. And on the Rust side, you have a box, which is uniquely owned. But the closest type in C for that is just a pointer. There is no really any difference between these two things. They're just objects in the heap. So you convert your OCaml reference to a C pointer through the FFI, and then you end up on the other side as not really anything in particular, just sort of this raw pointer in Rust that you have to remember came from OCaml and has certain obligations with the garbage collector, such as managing roots. And then vice versa, if you go from the Rust side, you have a uniquely owned box and you send it through the CFFI and you end up on the OCaml side with just some sort of raw pointer type that you have to remember to free. And this whole sort of region is just unsafe, unchecked. If you forget stuff, you end up with memory safety errors. And yeah, nothing in the compiler tool chain is preventing you from messing this up. So there's some prior work on improving the situation. So the prior work is a language called RichWasm, which was published in 2024. And the approach taken by RichWasm is that instead of just having one pointer type at the target level, you actually have two distinct pointer types corresponding to GC and manually managed references. And by keeping these distinct at the target level, it's not critical to safety that the source languages understand the other's memory management style, because the target language does understand it, and it will check that you're using the references correctly and that you aren't mixing them up. So as long as each individual source language has the ability to translate the types to the right target type, then the RichWasm type checker will ensure that it's handled correctly, it's memory safe. Now this is kind of interesting because now we have a single language with that supports two different memory management styles. So it actually has two different heaps. It has both a garbage collected heap and a manually managed heap, and because we want shared memory interrupt, those heaps actually interact with each other. They support cycles between them. And that has some interesting implications on what the runtime has to support. For example, the garbage collector has to understand how to free manually managed memory, because it could own manually managed memory, and when it's time to collect, it might need to free some stuff there. And this is why, incidentally, why RichWasm does not use WasmGC, because it does not appear to provide a mechanism to make this interaction work well. So, right, so the story in RichWasm is that you have your two source languages and you compile them both to separate RichWasm modules. And then at the RichWasm level, there's a module system. You can import, export things from each module. And right, the benefit of using RichWasm, that now you have this stronger type system that gives you memory safety. It also makes the compilation slightly harder because you have to generate code that passes the type checker, but you get the benefits in exchange. And then when it's time to actually execute the code, you have to compile all of the RichWasm modules that you want to interop together as one giant compilation unit. And you compile this down to a final WebAssembly binary. But at this point, it's no longer possible to import or export or otherwise link with any other module. Or to be more specific, you lose the memory safety guarantees at this point. The result from RichWasm is that you get memory safety guarantees if you link at the RichWasm level, but once you've compiled, there are no more guarantees with linking with arbitrary WebAssembly code. But to sort of make this situation better, because it is desirable to be able to link with other WebAssembly modules, both from that were compiled separately from RichWasm or just came from some other compiler. What we want to do is define an ABI at the WebAssembly level. So first, quickly, what is an ABI? So the Swift language defines it as the runtime contract for using a particular API or for an entire library, including things like symbol names, calling conventions, and type layout information. And I think this is what most people think of when they think of an ABI, is its calling conventions and data layout. But we also prefer to think of it as in a slightly richer sense. We want to include information about memory ownership as part of the ABI, so that if you are not using a pointer correctly, that should be considered an ABI violation. And so how do we specify an ABI? So one approach is, this is the most common approach, is to just use prose. So you describe the ABI in English as just part of the documentation, and a human has to interpret the specification and say, yes, this program is ABI compliant, or yes, this compiler produces ABI compliant code, and that's a subjective manual process. Another approach used by Wagner et al. Published in 2024 is called realistic realizability. And this is essentially a logical relation where it is indexed by source types, but it is inhabited by sets of target configurations. And by target configuration, I mean states of the target, like abstract machine, so like the code being executed, the stack, the heap, that sort of stuff. And because this is a logical mathematical object, you can now reason about it formally, and you can prove that a program is ABI compliant if you treat this definition as being itself an ABI. Right, and so how this works is that you have a source language with some source types, and you interpret your source types as these sets. And here the ... like what counts as being part of the set, can use program logic, you can use a separation logic, you can reason about resources. And you can think of the interpretation of a source type tau as being the ABI for tau. But to really benefit from the safety guarantees that you get from having a strong resource-aware ABI is that you want to prove that your compiler from your source language to your target language actually emits code that is in the ABI. So to do that, you write a proof, and that can be quite a complicated proof. And also, you have to reason about this separation logic, these separation logic things like directly, which is a lot of compiler writers don't want to do that. So our idea to make this situation a bit easier for compiler authors is that we will insert RichWasm in the middle of this compiler pipeline. And we will define a realizability model for RichWasm types inhabited by WebAssembly terms. And we will also write a proof for our compiler that our compiler, if given a well-typed RichWasm input program, always produces WebAssembly code that adheres to the ABI. And actually, in order to do this, we had to completely redesign the RichWasm language to make it possible to define a realizability model for it in a reasonable way. So we call that RichWasm 2.0. And so what the source language compiler author has to do is write a type-preserving compiler to RichWasm. And as part of that compiler, they have a type translation. So they translate their source types into RichWasm types. And then you can just like link these two things together, like chain them together, and you get a WebAssembly ABI for a source type tau by just taking the type translation, the interpretation of the type translation of tau, where you provide the type translation, we provide the interpretation. And now this is a WebAssembly ABI, so now you can link with other WebAssembly modules. And if the other WebAssembly module was compiled from our RichWasm compiler, you get that the linking is safe for free. That comes from our proof. But if you're linking with some arbitrary WebAssembly module, you can still prove manually that it is safe to link if you want to. Right, so in terms of sort of compiler engineering effort involved on a large scale, the idea is that there is one compiler from RichWasm 2.0 to WebAssembly that we write. And then there are many type-preserving compilers from various source languages to RichWasm. And right down here, there's some complicated, gnarly proofs involving separation logic, semantic models, proofs written in rock. And it's OK that this is hard because we do the hard work for you. We get this out of the way because we are researchers. We can deal with these complicated things. And then the compiler engineers just are up here writing their type-preserving compilers and picking and choosing types from the RichWasm 2.0's, from the type vocabulary of RichWasm 2.0 in order to encode their ABI choices. So just to quickly go over some details of RichWasm, it supports polymorphism for functions. And as part of the polymorphic quantifier, there is a kind constraint on types. And this kind includes representation or size, depending on if it's a WebAssembly value type or a heap type, type in memory. And it also includes some details on like resource management, whether you can copy or drop something. This is inspired by the kinds or calling conventions paper. And right, so this sort of kind system was necessary to facilitate an ABI because we need to, we don't want to monomorphize because that would sort of mess up the ABI. So we have these monomorphism restrictions where you can use polymorphism over types, but you must be monomorphic in the representation. And the nice thing about this polymorphic setup is that you can now encode things like ML has a uniform representation. All of its types are boxed by default. And you can encode this by saying that, well, all of my polymorphic functions quantify over types that are in my my uniform representation, which is a pointer representation that's expressible in the kind system. Yeah, and for our model, we use iris, and specifically RichWasm. And just to give a flavor of some things in the model, a manually managed reference, or this is a RichWasm type, is interpreted as unique ownership of sort of a virtual heap points to. And a GC reference is that same points to, but now it's in an iris invariant, which allows sharing and sort of aliasing of the pointer. But these are abstract locations. These are part of like a logical heap. And where the actual ownership comes from is in the interpretation of the pointer representation. And this uses pointer tagging to distinguish, like, is it just an integer, first of all, or is it a heap pointer, in which case, which heap is it in? Because we have two heaps. And the sort of separation between virtual and physical allows the runtime to manage the lifetime, such as when the garbage collector has to collect manually managed memory. Things are in progress. So this is work in progress. The big thing that's still in progress is the proof of compiler API compliance. So we are proving that if you give us a well-typed RichWasm program and we compile it to WebAssembly, then that is in the model. That proof is very non-trivial and is sort of we're improving the ergonomics of RichWasm, let's say, as we prove it in order to make the proof a bit easier to do. And we also have a case study involving two source languages. One of them is a core ML, which is reflecting the garbage collected side of things. And one is a linear lambda calculus reflecting the manually managed linear ownership side of things. These compilers are type preserving, but we don't prove that they're type preserving. They're just unverified compilers. But we have, we're working on examples. And yeah, so to conclude, we're developing RichWasm 2.0 to make it easier to specify a memory-safe ABI for your language. There's two parts to it, and we do the hard parts, is our pitch. And that's it.
So we have time for some questions. Could the next speaker prepare himself or herself at the time that we do the questions? Are there any questions?
Do you want to connect?
Yes.
You said that you had to redesign RichWasm to make this work. Could you elaborate a bit of what the problems were with the original version?
Yeah, so the main issue was polymorphism. So the original RichWasm 1.0 had to monomorphize all of its polymorphic functions as part of compiling to WebAssembly because it had like a very expressive form of polymorphism. So what we had to do was add these monomorphism restrictions with the kind system to make the code generation more tractable without monomorphization. That was the main change.
Thanks.
Any other question? I think we can thank the speaker again.